Professor Manu Pratap Singh sir. So let's quickly get started. So in this talk, I will walk you through the following section. First of all, we are going to see the introduction part where I will brief you about the background, and then we will discuss what motivates us to take this particular domain, and then very short literature review I will discuss with you all, and then we will see the methodology we followed, and then the result and discussion part, and finally we will conclude with key contributions and future possible work. So, antennas are truly the cornerstones of modern microwave technology. Without antenna, our mobile, satellite, even IoT devices, they will not work. So, I can say, you can think of them, they are the voices of our devices. They are the only ones that transmit and receive signals. So without them, our devices will not work. So like this, you can understand how important they are. Now, among many different types of antennas, microstrip patch antennas are the extremely popular ones. Why? Because they are compact, lightweight, low profile, and very easy to fabricate, and that's why you will find them in very wide range of applications, starting from mobile and satellite communication to radar application and medical equipments, and even so many other IoT devices. Now, on the right hand side of the slide, you can see the structure of microstrip patch antenna. On the top, we have a very metal patch, thin metal patch, which is placed over dielectric substrate, and beneath that there is ground plane. So this is a very mostly commonly used rectangular microstrip patch antenna. Now, since I am talking about rectangular microstrip patch antenna, it doesn't mean that other shapes are not so important. We also have circular patch antenna and triangular patch antenna. They are also very equally important depending upon the application. But right now we are talking about rectangular because they can be equally mapped to different structures. As you can see, a circular patch with radius r can be presented in rectangular patch of length 2r and w pi r by 2. So that's why we are going to just talk about rectangular patch antenna. Now, what motivates us? When we talk about microstrip antenna, for real world application, we don't only focus about shapes and size that we consider, but more precisely, the control over the resonant frequency. If the frequency is off, then our devices will not work, poor communication, and it may lead to the failure of the devices. So, let's look at the challenges. So, the first is conventional method. So the first one is conventional method. We have analytical formulas are available, but these are only approximations and often less accurate. Then we have electromagnetic simulation, which are very much accurate, but they are extremely time consuming and computationally expensive. And if we go dive much deeper in full wave characterization, then there we used to solve Maxwell equations, which requires lots of calculus and derivation. So now the next is growing demand. So I will quote a very popular example, or very common one example. Recently we all have seen India-Pak war, right? And what we have observed there, that was a different kind of war that we have seen in the past, because there was a very, because we have used drones, and in drones, the antennas are the major component because they are compact, efficient, and accurate. So the antennas are going to have a very strong demand, and then to overcome all these challenges, we have reliable alternatives. Like, researchers are exploring on all these alternatives for designing microstrip antennas, like neural networks, evolutionary algorithm, fuzzy logic, and in our case CNN, because it is a special class of deep learning networks, and we are going to analyze and design in our case using CNN model. Now this is a very short review. These papers I am displaying because we have compared our work and a circular, triangular and rectangular microstrip antenna, and they have used some machine learning algorithms like delta bar delta or back propagation and extended delta bar delta. Then another paper we have also taken into consideration where they have used PTS algorithm, one of the another machine learning algorithm, and then another paper where they have taken convolutional neural network, but what they did, they applied the parameters as binary matrix to that convolutional neural network. So we are going to compare our work with all these papers. Now let's quickly get started with the methodology. So the dataset used for this study consists of 33 measured configuration of rectangular microstrip antenna, and this dataset has been taken from the work carried by Kara in 1996, and this is a standard dataset which has been used. But 33 sets is a very small amount of data sets for deep learning. So we have used data augmentation where we have varied the parameters by plus and minus 2% of tolerance, and like this we have generated 8019 data sets, which we have divided 81% for training and 19% for tests, so that our model can learn well and generalize well. Now this is the key innovation in our work, is how we represent the antenna parameters. Traditionally, these parameters, length, width and substrate, they are treated as raw numerical values, but instead of directly feeding these to the model, what we have did, we convert them to RGB image. But why we did this? Because convolutional neural network are exceptionally on the left hand side of the slide, there is a 2 by 2 RGB image where each color channel is representing one parameter. As L is represented by red channel, W is represented by green channel, H is represented by blue channel, and epsilon R is represented by gray channel, which is the combination of all the three channels. And for RGB image, what we did, we used the four basic parameters which are L, W, H and epsilon R, and we also derived some more parameters like aspect ratio, patch area, effective dielectric constant and all. And like this we have created a 4 by 4 image and a 2 by 2 image. And now we are going to develop two models, one for 2 by 2 image and one for 4 by 4 image. So let's get started. So these are the hyperparameters that we have taken into consideration for a model. This model is for 2 by 2 image where we have fed the input parameters. Just conclude, I am going to conclude. So where we have fed the input image to the model, then we have 3 convolutional layer, 2 fully connected layer and 1 output layer. And then after that, this model is for 4 by 4 image where the model is also capturing the relationship of the images, and we have also gave derived parameters as input. So this is the most powerful in working, and this is the sample of data that we have created. And here you can see that the training and validation laws are very good in performance. And now see, this is the result and discussion part. Here you can see the regression for 2 by 2 and for 4 by 4. And in 4 by 4 you can see that the points are very much on the perfect regression line. On the left hand side of the slide you can see the real frequencies are and the predicted frequencies, they are much lying very close. And the most important part is the APE that we are getting, which is 0.32%, very small compared to all the work that we have already published in literature review. So our work is quoting 0.32% APE, which is much lower as compared to the others. So Here we have achieved high accuracy, 4 by 4 encoding outperform traditional method, balanced accuracy, and in future we can take this approach for multi-resonant antennas also. So we can carry out this process for multi-resonant antenna also and for larger data sets. Thank you.
Any questions from the audience? Okay. My question is,
Yes, sir.
what's your research contribution to the society through your research?
Sir, since my particular domain is for microwave. Sir, this work is particularly for microwave domain, and as I have already mentioned that antennas are the very essential part of any devices that we are using nowadays, whether it's mobile communication, satellite communication, or IoT devices which have been used a lot. So the commercial industry demands that we need very low, compact, very accurate, very efficient antenna or filters like this. So like this we can provide, and their designing process is very complex and time taking. So using AI, this time consuming process can be made very efficient and small. Okay, thank you, sir.
Thank you, ma'am. Now I'll call upon Siddharth Chordia, whose paper ID is ICF 25160. He will be giving the PPT online. Offline. Okay. I'll be calling Reena Garg, ma'am, whose paper ID is ICF 25385. Her topic is Review and Comparative Study of CNN and Transformers for Fingerprint Recognition and Iris Recognition.
Thank you, ma'am. A very good evening to all the respected dignitaries and all present here. I am Reena Garg and I am going to give my presentation on this topic, review and comparative study of CNN and transformers for fingerprint recognition and iris recognition. This is going to be the outline of my presentation, including introduction and so on. So first of all, what is a biometric recognition system? It is basically an authentication system that authenticates a person as per the biometrics. So it is widely used in today's world in almost every area for getting the access to, for the restricted areas, application accesses, or to get the access of secure data. So basically, our BRS or biometric recognition system includes certain steps including pre-processing, feature extraction and classification. So we have a numerous biometric recognition system whose performance is basically depends on the classifier that we choose, that is again bounded with the feature extraction. The feature set, the more the relevant the feature set will be, the more the performance the classifier will give us. So for numerous classifiers, I am restricting myself towards the deep learning models. It includes CNN models as well as transformers. CNN are the most widely used neural networks, whereas transformers are the most recently used deep learning networks. So convolutional neural networks basically extract the pixel to pixel connectivity. It access the local features, or we can say the patterns hidden in the pixel connectivities. So this is the architecture, normal widely used architecture. It mainly includes some convolution layers, max pool layers with the addition of fully connected layers, and at the end we have an output layer that is basically a softmax layer. This is the architecture for vision transformer. It multi-head self-attention mechanism is used, that is used to extract global features. Basically it divides an image into the partitions of patches. These patches are passed to the transformer encoder and gives the classification results. This transformer encoder is basically, this is the architecture of a transformer encoder that is used. It does not include any convolution layer, but it includes multi-head attention and MLP. MLP is for multi-layer perceptron. Next is swing transformer. This is an advanced variant of vision transformer that learns attention-based features more effectively as compared to the vision transformer, as it introduces a hierarchical architecture. That is, the model goes deeper for the patches, and patches are progressively merged. Initially, it 4 cross 4 size of 4 cross 4 pixel is used as a single patch. In later layers, they are merged together to give a more bigger patch. This is the architecture of a swing transformer encoder. So basically, fingerprint recognition is the most widely used and most prominent due to its uniqueness, universality and permanence. Publicly available data sets we have for the fingerprints, they are summarized here. This is the literature review for fingerprint recognition for the last 6 years, 2019 to 2025. Iris recognition, it is the most reliable biometric due to its long-term stability, resistance to duplication and uniqueness. The data sets that we have available publicly, these are summarized here. This is the related work for iris recognition. So if we compare our CNN models versus transformers, so we can conclude CNN models apply convolutional operations to learn local patterns, special features and pixel-to-pixel relationships from fingerprints as well as iris images, whereas WIT and transformers, swing transformers employ multi-head self-attention mechanisms to capture long-range dependencies for global structure information. Again, CNN may give higher performance in terms of accuracy as it accesses local features as compared to transformers, whereas due to the convolution layers, CNN model is computationally more expensive and time intensive in terms of it may include, it may take hours in training in comparison of transformers. With CNN models, we require heavy pre-processing and extensive data augmentation for small data sets, whereas transformers may be trained with smaller data sets without requiring too much pre-processing or augmentation. And CNN are most accessible as the availability of rich literature. We have numerous pre-trained networks and well-established architecture. And we can conclude transformers improves robustness against distortions, rotations and noise, and it can capture local features as well if we reduce the size of patches. Fine tuning is less demanding with transformers as available widths and transformer swing are pre-trained already. CNN can be integrated with transformers to have a fusion of local features with global features. So we can conclude that CNN models are highly effective in capturing detailed local patterns. Transformers offer better scalability, efficiency and robustness. Integrating CNN with transformers produces a more reliable and cost-efficient solution for BRS. Hybrid model produces a richer and more discriminative feature sets. In future work, integration of transformers, new variants like castling weight, IE weight, efficient weight, IF weight, even MEMBA with CNNs may lead to the development of more robust and more scalable BRS. These are the references I have included. Thank you. Any question? for single biometric. Yes, sir. I have included, actually, in this paper, I have taken 40 to 45. Otherwise, I have researched about ECG biometrics, about voice biometrics also.
Any other specific parameter chosen by you for the analysis?
Yes, sir. As per the performance plus the time it consumes. Thank you.
I want to call Sir. Now I want to call Sir Dr. Aditya Singh, whose paper ID is ICF 25885 and paper title is a multi-valued ANN based solution to inverse modeling challenges in microstrip antenna.
Thank you. Thank you, ma'am. Hello, everyone. My name is Dr. Aditya. I am from the Albag Educational Institute. Today, I am here to present a conference on the topic a multi-valued ANN-based solution to the inverse modeling challenges in microstrip antenna. So here are my outlines of my presentation is, first I will introduce the area of my work. After that, what motivates me to work in this particular domain we will discuss in the motivation part. Then what is the objective of my work. After that, what problem I consider to work in this particular paper we will discuss in the problem part. And at the last, we will discuss the resultant discussion, or we can say resultant conclusion. So over the past 3 decades, the emergent commercial, or we can say civil and defense market of the wireless communication has led to explosion of interest and opportunity for designing the microwave components, or we can say different types of microwave components. This is mainly because of the application in the military and civil domain. In the military applications, it is mainly used in the radar and electronics warfare system. As we can see, in the civil purposes, we use it in the mobile and satellite communication. And over these, the advantage of the microstrip antennas are listed here. You can see their simplicity, low manufacturing cost, lightweight, low profile, reproductivity, reliability, and easy in fabrication. So what motivates me to work in this particular domain? Now, the conventional way, as ma'am has already discussed this part, as the conventional way of microwave designing has also achieved a certain level of maturity. They have the complex issues while designing the parts, or we can say required more manpower or use more time consuming tools for designing such components. So this gives the space or opportunity to the other techniques like soft computing techniques. So this research is mainly focused on the advanced computational method which can be used for designing the microwave components. Now the objective to solve inverse modeling problem for while designing the microwave and millimeter microstrip devices using soft computing methods. So this is my problem. The approach based on ANN to tackle multi-valued inverse modeling problem in microstrip antenna. In this, first we discuss the geometry of the printed rectangular microstrip antenna. After that, we will discuss the modeling techniques which we used, the forward modeling, the inverse modeling. Then what is multi-valued. After that, how ANN work and the proposed ANN model. In the 5th part, we will discuss how the output of the ANN model will be selected for the valid values. And at the last, we will see the result. So this is the geometry of the rectangular microstrip antenna, the top view and the side view of the microstrip antenna with coaxial feed. Now, the modeling techniques. We have a two modeling techniques. First is the forward model and second is the inverse model. In the forward model, if you see, we use the physical or we can say the geometrical parameters as the input and get the electrical parameters as the output. While doing or we can say going to the inverse modeling, we simply swap the input parameter as the output parameter and output parameter as the input parameters. Simply. In this, the input is the electrical, and with the feeding the electrical parameters, we get the physical dimensions also in the inverse modeling. Now what is multi-valued? As you can see, with the help of this example, I write input are the same but output is different. As you can see in the serial number 1 and 7, the Q effective value is 99.78 and you are getting the W is different for both the both same input 250 and 400. With the help of this graph, you can easily understand this. On the inverse modeling, you have a dual input over the single input values. In the forward, we have a separate individual values corresponding to the inputs. This is the experimental data for the rectangular microstrip antenna. We generate these data with the help of the tolerance of 2%. We generated 8,019 data sets, in which we used 55% data for training and rest of 45% data for testing. As we know, the structure of the biological and artificial neuron, this help, or we can say this is the mimic of the human brain. How we behave, this will also behave like a human. This is the mathematical model. This is the, we can say, the analog between the biological and artificial neural network presented in this table. You can see this is the proposed MLP model, multi-layer perceptron model. As you can see, the representation of this MLP is 3, 40, 50 and 2. It means we have a 3 input, 40 and 50 are the hidden layers. We can say the inputs in the hidden layers, and at the last we have a 2 output sets. As you can see, we are getting 2n. It means we are getting the number of output values, n number of output values. After that, we will select it what values we can consider or what value we can call it dummy. That's why I write it here x1, x2, xn. So this is the proposed model for selecting the valid value. As we started giving the inputs to the inverse model, as you can see, input x, and we are getting the y, y1, y2, yn. These are the outputs. Then this output is given as the input to the forward model, and we are getting the z. And this, in this part, we are computing the error. If this error is relatively close or acceptable, we will consider it. Otherwise, this value is counted as dummy. If this value is valid, we will move, go forward, and this process is end up. Otherwise, this process is repeated until and unless we get the desired response, or we can say minimal error. This is the proposed training and test error function which we used, and this is the result. As you can see, the graph, this is the we can say the comparison table of different method, direct method, or the proposed inverse modeling methods of the rectangular microstrip antenna. As you can see, the graph is decreases very sharply, and at the proposed 7 values, we are getting the minimum error like 0.7478. Thank you.
Okay, is it possible to use as the real case scenario for your research work?
Yes, sir. This is we used in the we fabricated this rectangular microstrip antenna, and we used this training set, or we can say the multivariate problem, and designed this.
Have you implemented anywhere?
Yes, sir.
Is it successful?
More or less close, not precisely, we can say.
What is the main benefit of using your research?
Sir, while designing, see, we are giving the the advantage. We can switch we can get the forward model with the help of, we can say we get the antenna's dimension with the forward model, and we will also implement the inverse model to get the electrical parameters also.
Technically, is it possible?
Yes, sir.
Okay, why we cannot use the direct model instead of using the
What kind of direct, sir?
direct model? Direct evaluation. Inverse
Forward model.
Yeah, your model is inverse model.
Yes.
Why we cannot use direct model?
Sir, in the direct model, as you can, if you see here, in the forward model, we are giving the physical parameters. Physical parameters, it means W and L. And in the output, we are getting the dielectric constant, resonant frequency, and height of the antenna. Now, in the market, if someone is designing better, or we can say using the different type of technique which is more faster, now we are giving the dielectric substrate of values this, and resonant frequency I want this. Now you design the antenna precisely, which is the width is that and length is that.
Stop. Right. Right. Yes, you have used the MLP. MLP stands here for the multi-layer perceptron. And the architecture which you are using, I think this model will not support the perceptron. Because you are using the back propagation algorithm. And perceptron means that you are using the threshold function which has the output only 0 and 1. It means the output function which you are using is a non-linear and discrete. And if you are using the back propagation, you should have the linear and continuous and non-linear function. How the MLP can support this application? We think the MLP technique is not suitable for this. Instead of this, MLP should be the feed forward. Yeah.
Feed forward, okay.
Ziptron has the limited outputs, either 1 or 0. And here your outputs are continuous. Am I right?
Yes, sir.
So I think it should be changed with the neural network instead of the
Feed forward neural network, huh? Okay, sir. Thank you.
Next is the online presentation of Sir Siddharth Chordia. His paper ID is ICF 25160 and the topic is Hybrid CNN LSTM with soft attention for real-time ASL gesture recognition using mega pipe landmarks. Now I call upon Meghna Sharma, whose paper ID is ICF 25169, and the topic is feature extraction and classification of iris images using an autoencoder CNN model. लैपटॉप एक मिनट इससे इधर करो लैपटॉप अच्छा अच्छा
कहाँ मिलेगा मैम? So thank you, ma'am. Good evening, everyone. I'm Meghna Sharma, and I'm delighted to present my work on feature extraction of iris images using an autoencoder CNN model. This is the outline of my presentation, starting with the introduction and concluding with the conclusion. So iris recognition, why we chose the topic iris recognition? Because biometric iris recognition is one of the best biometrics method to identify an individual and it has numerous use cases like authentication in augmented reality, virtual reality, border control, security, surveillance, or mobile payments apps, mobile authentication. So I have stated some state-of-the-art models also, which have shown great accuracy for classification or identifying an individual, like YOLO and EfficientNet combinedly gives 98% of accuracy. Swin Iris Transformer gives around 99% of accuracy, and LW IrisNet CNN based model gives 99% of accuracy, and a hybrid model combining ANN and Dogman algorithm improves speed and accuracy. So when there is a progress, there are still some challenges. So let's look what are the challenges. So if we talk about the traditional methods, so as we all know, the size, dimensions and volume of data are increasing day by day. So traditional method absolutely don't work well with the current data we are obtaining or getting. They are also susceptible to outliers, meaning if there is a noise in the data, they won't give you correct results or even fail to work. Also, they are computationally intensive. Or if we talk about the deep learning are good for feature extraction, but what is the problem with the deep learning models? That they are computationally expensive, and most of the deep learning models don't work well in the real time. So our motivation was simple. We want to create a model which is accurate and as well as computationally intensive, which can be implemented on real time, meaning which we can use them on the go. So this is the proposed method. We use autoencoder and CNN. We combined autoencoder and CNN, used autoencoder as feature extractor and CNN for the classifier. So we gave input to the autoencoder raw image of iris, fed to the autoencoder, and then convolutional layer and max pool layer and bottleneck layer. After bottleneck layer, we obtained the encoded features of the images, which is then passed to the decoder, and the input and we reconstructed the input to check if the features that we obtained from the bottleneck layer are worth it or not. This is the explanation of our autoencoder, step by step overview. I can say input image, we chose an RGB image, so the size of this, and then convolutional layer which applies kernels or filters to extract the lines, shapes and textures from the image. Maxpool layer reduces the size for handling the data better. Bottleneck layer, as I said, obtain the encoded features, meaning the most important and highlighted feature of the image. Then upsampling layer again reconstructed the input to check if the features obtained are good or not. This is the diagram of our classifier, meaning that CNN model we use as classifier. In here the input to this classifier is the encoded features from the autoencoder, meaning encoder part from the autoencoder. Then it is passed to the convolutional Maxpool blocks. Then flattening layer is applied for making the data in one line long, and then batch normalization is used for stability. And then it passed to the softmax layer for classification. This is the step-by-step overview of our classifier, which I've already explained in the diagram. This is a complete network. I could just combine both the diagrams. So the data set which I used is the IIT Delhi Iris database version 1. It has 202,240 images in total, which I have done pre-processing. I reduced or resized the images in 2 cross 224 into 224 and then split the data into 7:3 ratio for 70% of the data for test training and 30% for the testing. So results, I trained the autoencoder for 25 epochs with the batch size of 32 and Adam as the optimizer and binary cross entropy as the loss function. And CNN, I trained CNN for 30 epochs, again the same batch size, and loss functions I use here is categorical cross entropy. So we can see we obtained MSE of around 0.0037, which shows that our autoencoder is working really well, meaning it is encoding or obtaining very good features. And through the graph you can also see the validation and training loss is decreasing in around only 25 epochs. So it is working well. This is the original versus reconstructed eye images, original images in the above row and reconstructed images of the autoencoder in the below row. It is visible that autoencoder is almost constructing nearly good images around as input, as the original input, and this is a result of classifier. Similarly, loss and training loss and validation loss in classifier is also decreasing in 30 epochs, which is meaning our network is working well. Performance metrics I use here, we obtained around 95% of accuracy, precision of 96%, recalling of 92%, and F1 score of 92%, showing that our model is working really well. So confusion metrics I showed here, top 10 correctly classified and top 10 misclassified classes, and we can see correctly classified classes are more, meaning our model is good. Concluding, our autoencoder extracts compact and meaningful iris features with the MSE of 0.0037%. CNN achieves 95% accuracy, showing that it is classifying the data well, and precision and recall shows reliable classification, and model shows strong recognition ability with few misclassification, which will be improved in our future work. We are currently working on variational encoder in our paper, extension of this paper, so it will improve, I guess. And this is the references I use for the support my study. Thank you. Yes, sir. So we use autoencoder for feature extraction, because autoencoder takes extract the highlighted features, important features only, and we have reconstructed the images through the autoencoder, and the reconstructed images were very similar to the input images, which shows that our autoencoder is building input very well, extracting good features. So it can, if we work on it more, so it can classification accuracy will improve. Thank you, sir.
Now we are connecting now we are connecting to Siddharth Chordia. He is online right now with us.
Presenting my work on hybrid CNN and bilistium model with attention for American Sign Language gesture recognition. In this paper, in this research, in this presentation, I'll first start with introduction and motivation, the motivation that we got, the idea that we got. Then we'll move to the literature survey that we did. Then I'll propose a methodology that I've used and the data preparation, results and conclusions. There are millions of people with hearing impairities, and hence the American Sign Language recognition methods are very much needed, and for them to represent themselves in video calls and in conferences, say online meetings, in corporate meetings, etc. So and the American Sign Language gestures include both spatial, like the hand and pose movement positions, and their temporal sequence, like how they are moving over the time. Both aspects are simultaneously needed to be captured. In our literature review, first discovered that the CNN and LSTM hybrids are needed, CNN for the spatial features and LSTM for temporal dependencies like temporal time sequences. Attention mechanism provide provide the focus on the critical frames. We are using MediaPipe landmarks to track the hand positions and also the pose positions of the model, and all of them needed to be translated in the live feed. American Sign Language and Indian Sign Language, both and all the sign language are time dependent, so we are using bidirectional LSTM layer for long-term sequence modeling, and it needed to be CPU friendly and lightweight so that we can design it for mobile phones, smartphone and tablet users also. So our input is MediaPipe hand and pose landmarks. So we are extracting 3D landmarks like the 3D XYZ positions of hands, and both hands and the pose. MediaPipe landmark provide us the lightweight and robust model across all the lighting conditions and background variations. For example, and since we didn't find the appropriate publicly available dataset, so we are going to train the model on our own dataset, and we have taken inspiration from all these and we have created on the basis of this dataset, which is WLASL and others. Yeah. Let's talk about methodology. First, the input, which is the 60 frame sequence of media pipe landmark, comes in and is passed for the spatial pattern recognition in the convolutional layer. Then the bidirectional LSTM captures the changes based on the time, like the temporal dependencies, and then it's passed to the attention mechanism and then to the dense layer for the gesture prediction. The convolutional layers in with the 256 filter captures all the local patterns like the movement of all the x, y, z variables, and it is the normalized, and dropouts are added uh, for preventing overfitting. The bidirectional modeling is there for capturing the temporal dependencies, like so we can so that with varying speeds and varying lighting condition also the model can predict accurately. The attention mechanism provides the important weights focus on the most important segments. So we are using the basic soft attention mechanism so that it stays lightweight also, and also helps distinguishing similar gestures, like hello is like this, and if where is like this, so the movement of this finger is always there, so it can predict, but it can predict hello and also differentiate hello and where both. So our algorithm is like the input that comes in, then the features are extracted, and then the temporal modeling is there for, and then the attention is put to the most needed, what do we say, like where we need to focus, and then those are classified using dense and softmax layers, softmax attention, and then the output is calculated. For data we are using 17 classes right now. We don't have a very big corpus here, but our data set has 17 classes. 16 are the gestures, different gestures like hi, thank you, where, etc. are there. And one is the idle state, which is if I'm staying still, there is no gesture, so I'm in the idle state. The original data set each has 850 sequence, so 17 classes with 50 different sequences, like 50 sequences in each classes, and each sequence has 60 frames. The 60 frames are captured, and with 258 features as in the dataset, the landmarks with 258 landmarks. I have also run the augmentation, which is the mirroring rotating on the z-axis for different positions and variations, and also trim the sequence to 60 frames so that if the speed is very high, then it is extended to 60 frames only. The final data set is 68,000 sequences for model training. My experimental setup is I've used M2 MacBook Air with 8-core CPU, GPU, and 8 GB RAM. So it's a very lightweight setup, and no external GPU is required for the predictions and for training. These are the performance matrices I have used for evaluating my model. And this is the sample results. So it's correctly predicting drink as I'm doing the gesture. In real time, this is happening. And this is the comparison of our proposed model with the state-of-the-art models. We can increase this accuracy by involving transformers and all. So we have developed a hybrid LSTM plus CNN and attention mechanism type of model for American Sign Language. We have created the dataset, robust dataset with augmentation, and achieve 96% accuracy, which is already higher than the state-of-the-art models. And this model is very lightweight, and it can eventually work on smartphones, tablets, and other lightweight laptops also. It doesn't need heavy GPUs to process. So the conclusion is that we are developing a very efficient real-time ASL gesture recognition system, and future is that we can also include the facial features like expressions, the expressions that the person is speaking. So, and also we'll use transformer based architectures to improve the accuracy of the prediction also, and for temporal modeling also. And we can also we'll also be able to deploy them in the real world
Hello,
ASL translation
Siddharth.
applications.
Siddharth, your time is over. Sir, you want to
Hello?
ask some question? Okay, thank you, Siddharth. Next will be the
Yes, that's all. Thank you.
Next will be the online session, online PPT of Adarsh Maurya. His paper ID is ICF 25173 and the paper title is Particle Swan Optimization Based Feature Selection for Chronic Kidney Disease Prediction.
Uh,
Hello, am I audible first of all?
yes, of course, you're audible, sir.
So right now, I guess it's my turn to give my presentation.
Oh, so I'll stop the screen sharing.
Okay, Siddharth.
Thank you.
Well, just a second. So, good evening, everyone. My name is Adarsh Maurya. I am doing my undergraduate from Banaras Hindu University, second year. My major is botany, and today I am representing my paper on particle swarm optimization based feature for chronic kidney disease prediction, and my co-authors are Arpit Pathak, who is a second year student from IIIT Bhagalpur, and my third author is Bhanupriya ma'am, who is a faculty at IIIT Bhagalpur. So let's start this. So here is our outline of my presentation. First, we will start from introduction, then problem statement, then we will move to related work, proposed methodology, result and discussion, conclusion, and at last we will go to references. So CKD is a progressive condition that just makes the kidney loss its function. So globally it's about 700 million people with CKD, and if we combine kidney failure, then the number is around 850 million. In US, about 14% of people have CKD, and like many people are not aware of CKD, approximately 90% of the people are not aware of the chronic kidney disease. So early detection is very important in this disease. There are two major problems that why they are not detecting it early. First is like too many features without proper selection. The CKD shows up multiple symptoms, so that some trained specialist the person has to go to a trained super specialist in order to get it detect early. And second is like the people don't take it seriously. Like when they get symptoms of CKD and all, they just don't go to doctors. They just go to normal doctors having less qualifications, and it is also difficult to detect, like first of all. So that's the case. Okay, moving on to next slide. Earlier, the related work that has done for the detection of CKD is like PCA plus XG boost. These are some models that are used earlier for the detection of CKD. That is PCA plus XG boost and the accuracy is 99%. ANN plus feature selection. ANN is automatic neural network that uses artificial neural network that uses a strong predictive power, and it performs the classical models. So and third is neural networks with feature selection. Fourth is ensemble deep learning models. This showed a high accuracy, like it showed like 99.7%, and some methods like Boruta plus KNN which reached 100% accuracy. So now we are moving towards my methodology of CKD detection. We have used the UCI CKD data sets which has a record of 400 patients, and with 24 attributes. 250 were already suffering from CKD and 150 were non-CKD. They were not suffering from any kind of kidney problems. I'm getting notification to open my camera, but my laptop camera is not good enough. So is that a problem? I guess. Can anyone confirm? Okay, so we will move on to next thing. So we were like, in my model, we have taken the data set of 400 patients with 24 attributes. 200 were suffering from CKD and 150 were not suffering from CKD. They were completely well. Then we applied the particle swarm optimization feature, which is the heading of our paper, like what we are doing with it. So we have tested 5 machine learning model. First one is random forest. One second. Yes. So we have used 5 ML models: random forest, gradient boosting, SVM, logistic regression, and ANN. Random forest gradient boosting, SVM means support vector machine, and ANN is artificial neural network. So we have evaluated it under 5-fold, 10-fold, and 15-fold cross validation. So this is our results before feature selection. Before feature selection, when we had done for 5 folds, the RF, random forest, and GB, which is gradient boosting, has the highest accuracy, like 99.8%. SVM and ANN were competitive, 97-98%, and LR, logistic regression, was the weakest. But after our particle swarm optimization feature selection, the RF, random forest, and GB gradient boosting were showing accuracy more than 99.7%, which is close to perfect. And ANN did not show any significant changes. It was already strong. So it remained just there, and LR, logistic regression, was also improved a little bit. Earlier it was 85, and now it went up to 96%. And this is the confusion matrix here. 5-fold random forest means once you have applied the data, and 4 times you are doing the study over that data. So this is 5-fold and 5-fold gradient boosting, and then we have 10-fold, and then we have 15-fold. So this is the confusion matrix of random forest and gradient boosting, both of models. And prior studies only reported 85 to 100% accuracy using various classifiers. Our method, which we have used here, showed nearly 99.75% accuracy, and were really the best out of all methods till today. Particle swarm optimization based feature selection improved efficiency and performance of multiple ML models, and this we had gone to like 99%, and and that's it. Like, thank you. That's it.
Thank you, Adarsh. Next is online Abhi Ramis. His paper ID is ICF 25487 and the topic is securing the future of mobility, cyber security threats and migration
Hello.
mitigation strategies in connected and autonomous vehicles. Adarsh, close your presentation. Abhirami, please
Hello.
open your presentation, share your presentation.
Hello, ma'am. Am I audible? Hello, everyone. Am I audible? Can anyone just? Hello. I'm done. So, please move on to the next person here.
Okay, now we have 10 minutes tea break and then afterwards we'll meet. You can all enjoy your tea, that is all outside there.